So hello everyone, welcome back to PC 301 workshop, and we start with the third talk of the day. And we have with us once again Karthik CS from New York University, and he'll be talking on hardness of approximation meets parameterized complexity. So thank you once again for joining us, Karthik. Over to you now.
Thank you. So this is the second lecture. And as I said, I wanted to slowly introduce the area of hardness of approximation and parameterized complexity. And let me recall the global outline. So yesterday I defined some key problems of interest in parameterized complexity, introduced a bit of coding theory. And today we are going to use everything that we saw yesterday and actually prove some hardness of approximation results from scratch. And tomorrow we are going to prove some actual applications of the results that we use. So we'll prove hardness of approximation results today to two problems, MaxCover and one-sided Biclique, and then we're going to use these in-approximability results to prove hardness of approximation results for other problems. So that will be tomorrow. So today's outline would be, I'll first recap what the definition of MaxCover is, and I will then define MaxCover with some additional property, which is called projection property. And then I will show how to create a gap, like start from an instant in which there is no gap at all, and then create a gap on the way. And similarly, for I'll try to do the same for one-sided Biclique, where I'll first recall the definition and then show how to create a gap. And the techniques for both of them are very similar. And then I'll discuss a bit about how, in general, how this technique is and how to do such things for other problems and things like that. Okay, so let's start with part one, gap creation in MaxCover. So let me start by talking about the definition. So in MaxCover problem, if you recall, there's a bipartite graph on partite sets U and W, and the WIs, which are a collection of supernodes. So it's a collection of nodes in W. So that's called the right supernodes, WIs, and the UIs are called the left supernodes. So you can think of as W being partitioned into K parts. Each part is called a supernode, and then each supernode contains a bunch of nodes, and the same with left. And we define a labeling of W is picking one representative from each supernode. So in total, you pick K nodes in W, one from each WI, and that is called a labeling of W. And we say that a labeling covers a left supernode UI if there exists a node in UI which is a common neighbor to all the elements, to all the vertices in S. So to all the K vertices. So if it's a common neighbor, then we say it covers this supernode UI. And then given a labeling, which is these K nodes in W, one from each WI, the measure, the complexity measure we are interested in is the number of left supernodes that it covers. So the number of left supernodes for which in each of those supernodes there exists a vertex which is a common neighbor to all these K vertices in our labeling. And the value of the MaxCover instance is basically then you go over all possible labelings and you pick the one that covers the maximum fraction of supernodes on the left. And then the question we are interested in is, given an instance of MaxCover, which is a bipartite graph, determine if there is a labeling which covers all the left supernodes versus in the case where every labeling covers at most S fraction of the supernodes on the left. So when we are given this instance, we want to decide which one does it belong to. And we saw yesterday that this is actually W1 complete when S is this W1 complete, and even for the exact instance. And we also showed that there is a hardness of approximation results for this problem, which we're going to see now. And before I show the hardness of approximation result, I want to define MaxCover with an additional property called the projection property. So what is the projection property? It's a MaxCover instance as before, but we say that it has the projection property if the following holds. Now fix a supernode Wj on the right and fix a supernode Ui on the left. So you have fixed these two supernodes, and then you look at just their induced subgraph. Okay. So now the induced subgraph has, if it has the projection property, will look either like it's the complete, all the edges are there between Ui and Wj, or for every vertex in Wj, it has exactly one neighbor in Ui. So it either is one of the two things. Now, why is this called the projection property? If because if you had all possible edges between Wj and Ui, then essentially this is a redundant set of edges, because it doesn't matter which of the Wi's I pick, it will cover all the nodes in U, will be able to, Ui will be able to cover it. So there are many ways to cover it. So it doesn't really matter which one I pick. So we can, at least at an intuitive level, you can remove those. Those are not really your hard constraints if you're trying to solve this problem. Whereas if I fix any node in Wi, in Wj, then there is exactly one guy I have to pick in Ui in order to make sure that it's getting covered. In other words, it's a function. So you can think of this induced subgraph as defining a projection or a function. And this is exactly the projection property that exists in label cover instances in the NP world. So a projection property there is that there's a function from left to right vertices. So here too, it's the same. It's just that for the sake of some technicalities, we had to define it as allowing these redundant edges as well. So for instance, you can look at the two red set of edges. So if you look at UR and WK, you have all possible edges there. So that's fine. That part is fine. Whereas if you look at W1 to U1, it's a projection. So every guy has exactly one neighbor. Every guy in W1 has exactly one neighbor in U1. So this particular instance that we have has the projection property, because it either is one of this kind or the other kind. And why did I introduce the projection property? It's because we'll be reducing from the MaxCover instances with projection property with no gap to MaxCover instances with gap. And one might wonder if the projection property is too much. Maybe we showed that MaxCover is W1 hard, but maybe MaxCover with projection property might be easy. These instances might be easy, but it turns out it's not. This is fairly easy to obtain. So here's a proof that MaxCover with projection property is W1 hard. Take your standard k-Clique problem. So you're given a graph G on n vertices and edge set E0. As yesterday, we're going to create a MaxCover instance where the W's are all the possible k choose 2 edges of your k-Clique. So for each, so you have on the right all possible k choose 2 edges of your k-Clique, and on the left all possible k vertices of your k-Clique. And we just need to pick for each guy in each Wi an edge of the k-Clique, and in each guy here a vertex of the k-Clique. So your Ui is going to be n, which is so each Ui is a copy of the vertex set as before, and each Wjj prime is a copy of the edge set. So you have k choose too many copies. And notice that if I take this particular construction, then the only time I'm going to really care about what I put is when I have to look at the supernodes Wjj prime and Uj, or Wjj prime and Uj prime. Because in this case, I actually put the membership graph of G. And if it's not, then I don't care, right? Like I would just put all possible edges. So this is a reduction we saw yesterday, where for fix any Wjj prime, how do we introduce the edges in this MaxCover instance? So if it's Uj, then you just mark, okay, is this edge incident on this vertex? because uj is a copy of the vertex set, wjj prime is a copy of the edge set. You put an edge if this edge is incident on this vertex. Whereas if I had wjj prime and say uj double prime, which is not relevant at all, then you just put all possible edges. So just by the construction of the MaxCover instance, it has the projection property. So MaxCover with projection property is W1 hard. And so what we are going to show now is that we start with a MaxCover instance gamma naught, which has the projection property. And say the gamma naught has left supernodes U0, so U01 up to U0R, U0R, and the right supernodes W and edge set E0. And we're going to reduce it to a MaxCover instance gamma, which has the same W. So the right supernodes stay the same, except the left supernodes now change. So they either blow up or shrink. There is some transformation that happens on the left supernodes, and the edge set, of course, changes. So we have a reduction, which we are going to see, which starts from a MaxCover instance with projection property to another MaxCover instance, which might not have projection property, but will have a gap. What does that mean? It means that if my original instance, gamma naught, the MaxCover value is 1, that is, there is a labeling which covers all the left supernodes, then in my new MaxCover instance, there is a labeling of the right supernodes such that it covers all the left supernodes. So if it was 1 before, it's going to remain 1. Now, what if it was not 1? So I must say there exists like one, for every labeling of the right supernodes, I used to miss 1 of the left supernode. Then in the new instance, gamma, you're going to miss a quarter of the supernodes, a quarter fraction of the supernodes. So we have created a gap now. So approximating MaxCover in the new instance to a factor of 75% of the optimum is equivalent to solving the original problem. So that's what this implies. And more importantly, this is an FPT reduction, and the size blow up that we have is just 2 to the r times w times log q naught. So as long as r is a function of k, we are fine to start with, or at least you can even allow up to log n. And the reduction runs in time 2 to the o of r poly this thing. So as if r is like some function of k or something log n, it's fine. And it will be fine, it will be some function of k. Okay, so we are going to see this proof. And before I show the proof, I want to recap some of the coding theory that we picked up yesterday. And let's start with, let me just recap what all we picked up. A code is just some subset of q to the L. So you have L length vectors. In each entry, in each coordinate of these vectors, you write a value between 1 and q, right? And a code is just a subset of q to the L. It's just some bunch of strings. And the distance of a code is you take 2 strings of length L, you have entries in Q in each of them, and you look at how many coordinates on which I write different values. So the number of coordinates on which the 2 strings differ is the distance of between the 2 strings. And if you go over all possible pairs of strings within the code, then the maximum, the minimum distance between which pair it is, that is the distance of the code. So you go over all possible things and find the minimum. Again, a code is supposed to be something where you have a lot of, so it's supposed to be dense, so it's supposed to be a big set. So if you have q to the L possible strings, I want to pick at least q to the L over 100 or something like that. But at the same time, I want every pair to be separated on at least say L over 50 locations. So you want this contradictory property that it's both dense and well separated. And we saw that if q was 2, so you are just on binary alphabet, then if you just, for some constant row, if you just pick 2 to the row L many random binary strings out of the possible 2 to the L many strings, then you are guaranteed with high probability that it's a code with distance L over 4. So that means that any 2 strings will differ on L over 4 fraction of the coordinates. So this is what we saw yesterday. We also saw that if you didn't have binary, but you had more larger values, then you can look at Reed-Solomon codes, which are just evaluation of degree D univariate polynomials over FQ. So Reed-Solomon codes, we know that it's defined over the space Q to the Q for some prime power Q. And there are Q to the D plus 1 code words because you have D plus 1 coefficients and each one can take any field element. And the distance is Q minus D. And we saw this is essentially tight. So because any two polynomials can agree in at most D locations because they can have at most D roots, degree D polynomials. So we have managed to construct Q to the D plus 1 code words in the space Q to the Q with distance Q minus D. And notice how tight it is. So if you, for instance, put D equals to 0, that means that you want distance Q, right? So you want strings of length Q, which are at distance, which differ on every location. So obviously there are only Q possible things. It's the all ones, all two, and things like that. And the number of code words the Reed-Solomon code gives is also Q. Whereas on the other hand, if you wanted distance to be 1, that is D to be Q minus 1, then you have Q to the Q code words in Q to the Q. So that's tight. You have the entire space. So the Reed-Solomon codes are essentially tight, and the trade-off is also very smooth. So we will be using both binary strings above, and if you want larger gaps, we will use Reed-Solomon codes now. So this is a recap of coding theory. And now let's go back to our thing. So we'll be wanting to prove this theorem where we start from MaxCover with projection property and reduce it to a MaxCover instance which has a gap. So for this particular thing, all I'll be using is random strings in binary strings. So the threshold graph construction starts as follows. So you're given an input graph, right? So you're given the U0W, as you can see, the orange and the green ones. So that is your input MaxCover instance with the projection property. We'll come to the deconstruction later, but let me now talk of a construction from U0 and introduce this new thing called A. Now, U0 was part of the input problem, but I also think of every U0i, every left supernode, U0i, as my code C. So in other words, I think of every vertex in U0i, I associate to it a random binary string of length L. Okay. So now simultaneously, I'm thinking of it as as nodes in a supernode of a MaxCover instance that's given to me, and also as a code word, as a random binary string. Now, there is on A, I have L many supernodes. L is the same as the length of the vectors we took on the right side, the random binary vectors. And each AT, let's say each supernode in A, is all possible R values that you can, binary values that you can get. So it's all 0, 1 to the R. And now I need to tell you, when do I put an edge? When do I put an edge? When I pick U in UI, and let's say Q1 to QR in AT. So Q1 to QR are just all possible 0, 1 values. So Q1 can be 0 or 1, Q2 can be 0 or 1, QR can be 0 or 1. So when do I do it? So as I said, you have picked U in UI, and we have associated to U in UI a random binary string of length L. So we look at exactly the teeth position because we are interested in this Q1 to QR in AT. So we look at the teeth position of the string, and it's either 0 or 1. So if it's equal to QI, which is also 0 or 1, then we put an edge. So let me again repeat this thing. So what AT is really doing is checking that the teeth location of the strings that are associated are consistent. So that's what AT is checking. AT is really doesn't care about, AT doesn't look at the entire random binary string. It just looks at the teeth coordinate of these things. And what does U do? U doesn't care about all the possible code words. It is given one code word. So it's a way of sort of sharing responsibility. So each node in U0 is given one code word, and each node in AT is given one coordinate. And we are just checking if the code word and coordinate are consistent. So in other words, we are checking if the teeth coordinate of the code word ut, is equal to qi. Okay. So this is the construction. So this is what we call a threshold graph construction. So this threshold graph is between U and A. And this has some very nice property. So we are going to now see this property. If you pick any R guys, one from each of the supernodes in UI, and you take any arbitrary supernode AT, then there exists a unique common neighbor of these U1 to UR. Okay, so let's see this. So let's say that we picked one guy from each one of them. So we have picked in total R code words because there are R supernodes in U. And we picked an arbitrary AT in the left. The claim is that there exists someone in AT which is exactly a common neighbor to each one of them. And this is obvious because you look at the teeth coordinate of U1, U2, UR. Okay, so the teeth coordinate is going to be a bit 0 or 1. So in general, you have t bits because one from each of the guys you picked. And this t bits is going to be there in AT. It's going to be a vertex in AT. And just by definition of when we'll put an edge, it's going to have an edge to each one of them. So it's the common unique neighbor. So it's neighbor to every one of them, and it's unique. So the completeness just says that if you pick one guy from each one of them, then there is a common neighbor, which is also unique. So there's exactly one of them. And this completeness. And in the soundness case, it says that if you take any two vertices within the same supernode in UI, then there are at most L minus the distance of the code. So the distance of the code is a value between 0 and L, right? So there are L minus the distance of the code many supernodes in A which have a common neighbor. And this is obvious, right? Because if you take U and U prime, so let's say if you took U and U prime from the same guy, they are two code words. Now, the only reason they will have an edge, so if we go back in the definition, the only reason that U and U prime both have an edge, common edge to Q1 to QR is if UT is QI and U prime T is QI, which means that UT and U prime T agree on the teeth coordinate. So the strings, the code words U and U prime are agreeing on the teeth coordinate. But we know that these are well separated. These are random binary strings, so they can agree on at most like half the coordinates, right? So we know that's exactly why the distance of the code comes in, that they don't agree on a large fraction of the coordinates. So the soundness holds that if you pick any U and U prime from the same supernode, there are at most L minus the distance of the code, which are the remaining coordinates on which they can have a common neighbor. So we created, just using some simple thing as codes, which we just saw intuitively yesterday, we are now able to create this beautiful threshold graph with this property that, if you pick one from each, then you have a common unique neighbor for every supernode in A. Whereas if you pick two from the same supernode in U, then you are already not able to get a lot of common neighbors. So now let's go to the full composition. So we have between U and W our input problem, which is the projection MaxCover instance. And between U and A is this threshold graph, and U is doing sort of a double role. It's both being part of the input MaxCover instance with projection property and being sort of the base of this threshold graph, which acts as code words. So the UIs are simultaneously both nodes of the input graph and code words of the threshold graph. Now what we will do is that we'll eventually drop U and build a MaxCover instance with W and A. right? So I need to find a way to define edges between W and A, because we are going to drop U. And how do we do this? This is what is called the composition step. And the way we do it is quite simple. We take some W in W and say Q1 to QR in AT. So we have taken fix some supernode WJ, pick a vertex in it, say W, fix a supernode AT on the right and on the left, and fix some node in it Q1 to QR. When do we put an edge? We put an edge if there exists some U1, little u1 in capital U1. So for every supernode, there exists a vertex in U, such that if you look at U1 to UR, both our W and Q1 to QR are a common neighbor. You see? So if we have U1 to UR, so you have picked one guy in each of the U's, there exists one guy in each of the U's, such that both our W, which is picked on the right, and our Q1 to QR, which is a vertex in AT, are both common neighbors of U1 to UR. In that case, if this is true, if there exists such U1 to UR, then we put an edge between W and Q1 to QR. So this is the composition step. So when we do this, we have consistently built a MaxCover instance. I have to prove the correctness of this reduction. But this is how you start from this UW, which has projection property, and build this new instance between W and A. And now I need to show the correctness of the reduction. So completeness first. So let's say that there was some W1 to WK, which is an optimal labeling of gamma naught, which is our original instance. That means that it satisfied all the supernodes on the left. Now, clearly, there exists some U1 to UR, right? So, which is basically because its MaxCover is 1. So there exists some U1 to UR, one in each left supernode, which are common neighbors of W1 to WK. And now we just apply the completeness of threshold graphs that we had. That if you picked exactly one in each left supernode, then for every AT, there exists a unique common neighbor. Right. So we have managed to, and so we'll have an edge between this and this. So that's exactly why every right WJ is going to cover every AT. So from the completeness of the threshold graph and the fact that MaxCover value is 1 for the original input problem that we had, we are going to get the completeness part, that this W1 to WK is still going to be an optimal labeling for our new instance gamma. Okay. Now let's see the soundness of the reduction. So fix some labeling, W1 to WK. Okay. And what we want to say is that there exists some, because it's the soundness case, that means that if you fix W1 to WK and you looked at the original, the gamma naught instance that we had, there exists some UI which is not covered, right? So there is no vertex in UI, which is a common neighbor to all the k vertices of our labeling. This is just the assumption. But this is where the interesting part comes. We know that our instance is a projection instance. That means that for each W1, either it's a redundant thing, in which case we don't care, or it has exactly one neighbor in UI. So in other words, there exists some WJ and WJ prime in our labeling with neighbors, say U and U prime in UI, and U and U prime are different. So they have exactly one neighbor and they both go to different things. Now, the interesting case comes if A is a common neighbor, so if A in A is a common neighbor of both WJ and WJ prime in our new instance gamma, then it's easy to see that U and U prime are common neighbors of A in the threshold graph, because that's the only way we are going to have an edge. So when do we have an edge? We have an edge if, if we are able to reach from here to here through common neighbors. So if A is a common neighbor of both Wj and Wj prime in our new instance gamma, then there exists some U and U prime, but now they are not the same thing. U and U prime are different because we are in the soundness case. But nevertheless, they are both common neighbors of A. That's the reason we have an edge from Wj and Wj prime to A. This is by construction. And now we apply the soundness of the threshold graph, that if U and U prime are in the same supernode Ui, but they both have an edge, common neighbor in A, then that means that the number of such supernodes for which this is true is at most L minus the distance of the code. And remember that the distance of the code for random binary strings we just saw was L over 4. So this is at most 3L over 4 of fraction of the supernodes of the new instance. So we ended up proving this result because we started with a MaxCover instance gamma naught, which has the projection property, and we reduced it to a new MaxCover instance. And as we saw that there was a blow up in the U size. So from U naught, which had R supernodes, we now have log U naught, which is because the distance of the code, the rate of the code. And we have the same W. And if it was initially satisfiable that there was a labeling that covered all the left supernodes, the same labeling worked in the new instance. Whereas if before you were failing one, you were not able to cover one supernode, now you are not able to cover 1/4 of the supernodes. So this is what we got. But what if we want something stronger, right? Like now this is this rules out approximation algorithms that approximate to a factor 0.75 of the maximum. What if we want to roll out stronger? Then we just use a different code, like a stronger codes. That's it. So if you use Reed-Solomon codes, for instance, so the two differences are that you won't have A1 to AL because your L is now the same as Q. And it's no longer binary, right? So it's Q to the R. So it's not 0, 1 to the R, but Q to the R. But everything else goes through exactly the same. So it didn't really matter what the code is. Like we didn't use any explicit definition of the code. So you still put an edge between W and Q1 to QR is if there exists this U1 to UR in the middle, such that they're common neighbors to both W and Q1 to QR. So now the blow up will just be Q to the R instead of 2 to the R. And our completeness and soundness work exactly the same, that if you picked one guy from each in the threshold graph, then you have a unique common neighbor. Whereas if you pick two guys here, now notice that you just have a stronger guarantee that because before it was L minus distance of the code, now your L is Q, and the distance of the code was Q minus D, and D is roughly whatever the expression here is. So you have much smaller fraction of the codes in which nodes in which they have a common neighbor. So let me retell the statement that if you use Reed-Solomon codes, you start with MaxCover instance with projection property, and you reduce it to an instance where you have in the no case, if the MaxCover value was less than 1 for gamma naught, now you're going to get MaxCover value is less than log Q, log base Q U0 over Q. Right? And typically your U0 is size, say, log n or n or something like that. Now, even if it's n, then if you choose Q to be n to the 1 over k, so let's think of this setting. Q is n to the 1 over k. So log Q U0 is just k. So you have, in the yes case, you have MaxCover value 1, remains 1. And in the no case, if the MaxCover value was just less than 1, now it's going to be 1 over n to the 1 over k, which is sub-constant, right? So you have managed to pull the soundness down. So you're ruling out n to the 1 over k approximation algorithms. So you're saying that even finding an n to the 1 over k approximation algorithm is W1 hard for MaxCover problem. And your runtime is fine and your blow up is fine because Q to the R. So if your R was k, say, for instance, then Q to the R is n to the 1 over k times k in the exponent, so it's just n. So the blow up factor is n, so it's fine. So we managed to, so what I'm trying to say is that we managed to have a MaxCover instance with no gap and managed to get a gap of 1 versus 1 over n to the 1 over k. So like a very low subconstant. And we just used the code and the distance of the code properties. Okay. So now I'm going to move to part 2, and it's going to look very similar, at least the composition step. And we are going to talk of gap creation in the one-sided Biclique problem. So let me remind again what the one-sided Biclique problem is in this case you have a bipartite graph U and W, and what you want to do is find k vertices in W which have most common neighbors in U. Right? So for instance, you would want to find these 3 vertices which have the most common neighbors, whatever. So there are, as we said yesterday, there are a few differences between this and MaxCover. The fact that here there is no partitioning of W and U into supernodes. No, you can pick any k guys you want in W. And the notion here is no longer of covering a supernode, but number of common neighbors. And finally, we said that using color coding, one can reduce one-sided Biclique to MaxCover. So if you just use the standard color coding technique. So in other words, one-sided Biclique is an easier problem computationally than MaxCover. So the reduction we'll see now, which is going to create gap, has to be more non-trivial because we're proving hardness for a computationally easier problem, relatively easier problem. And that's why we're going to see that we're going to just using codes will not be enough this time. So we'll have to use something stronger. So let's start. I'm going to show you now a proof of Binkheilen's paper on Biclique. So we're going to see an FPT reduction from, okay, so that's a typo. This should be a k-Clique instance G to a one-sided Biclique instance gamma. So we're going to start with a k-Clique instance of, say, G, which is just a graph, and we're going to reduce it to a one-sided Biclique instance, which is a bipartite graph, such that the following holds. If G has a k-Clique, then so we're going to construct a Biclique instance such that you can pick k choose 2 instances on the right, which have n to the 1 over k common neighbors on the left. But if G had no k-Clique, then regardless of which k choose 2 vertices you pick on the right in our Biclique instance, in one-sided Biclique instance, it's going to have at most k plus 1 factorial common neighbors on the left. Notice that this is, if k is constant, this is again as the same kind of gap that we obtained for MaxCover. And our running time and blowups are fine. It's just poly n. So we're going to see this. So we're going to start with a k-Clique instance, which is just a graph, and reduce it to a bipartite graph, which is a one-sided Biclique instance, and show this gap. So we start from the k-Clique problem. And in the k-Clique problem, we have an input, which is a graph on n vertices and an edge set E0. So we're going to write this as a bipartite graph, where you have the edges of your input graph on the right and the vertices on the left. And you put an edge between an edge in E0 and a vertex in V if that edge was incident on the original graph. So it's just a standard membership graph. Now notice that if G had a k-Clique, then I could pick those k choose 2 edges of the k-Clique in E0. And if I look at their common neighborhood, like their total neighborhood, now since every guy on the right in W is an edge is incident on at most 2 vertices by definition, right? So it has a degree 2. You can see that in the picture, all the degrees are 2 of the vertices on the right in W. So if you take those k choose 2 edges that correspond to the k-Clique, then they coincide, their total neighborhood, the total number, not the common, the total neighbors. So you just take the union of all the neighbors of the vertices of the k choose 2 vertices. It's going to be k vertices. So you have these k vertices here and these k choose 2 vertices here, because the k vertices of the clique are the total neighbors of the k choose 2 vertices you pick here, because that's what they're incident on. So if you had, if you had a k-Clique, you can do this. You can pick these k choose 2 vertices such that the total number of neighbors here is just k. Whereas if G did not have a k-Clique, then regardless of which k choose 2 vertices you pick here, they're going to be containing k plus 1 vertices, because otherwise you would have had a k-Clique. So the total number of neighbors of k choose 2 vertices in W is going to be at least k plus 1 here. So just if you look at it as how many, if I pick k choose 2 edges, how many vertices do I hit? If there is a k-Clique, there is a chance you hit only k. But if there's no k-Clique, you will hit at least k plus 1. And we'll start from this bipartite graph. We need to keep this bipartite graph in our head. And there's another bipartite graph we want to keep. The V is the same V I had before. Okay. So it's the same V here that appears here. So now we build a threshold graph, which is a bipartite graph on n vertices and n vertices, which has this following wonderful property, that if I take any k vertices in V, they have at least n to the 1 over k common neighbors in A. Okay. But if I take any k plus 1 vertices in V, it has at most k plus 1 factorial common neighbors in A. Obviously, if you take one more vertex, somehow the common neighborhood, so now it's common, which means it's a neighbor of every guy, every one of the k guys or the k plus 1 guys. So if you pick k guys, there are n to the 1 over k vertices in A, such that they are a common neighbor to each of these k guys. But if you pick k plus 1 guys, then it's no longer n to the 1 over k, but it's k plus 1 factorial. There's a huge collapse that happens. So I'm not telling how to build this threshold graph, but let's assume that it exists. Okay, let's assume that we are able to find this magical graph on a bipartite graph on n vertices and n vertices. This is for k guys, a lot of common neighbors, k plus 1, very few common neighbors. Suppose we had this, then how does the reduction go? So the reduction is as follows. So our W and V was basically the bipartite graph we just built from the k-Clique instance, edges and vertices. And V and A was this magical graph that we assumed exists. And our Biclique instance will again be between W and A. So we're going to drop the V's. So how do we do this? This is going to look very, very similar to the composition technique we had for MaxCover. So what we do is that we take a vertex W in W, little w in W, and a little a in A. And if there exists some U and U prime, which are a common neighbor to both A and W, remember that W is of degree 2, so it has exactly 2 neighbors in V. And if both 2 neighbors go to A, so if they both have A as a common neighbor, so you have this C4, cycle of length 4 that's formed, then you put an edge between W and A. So you're going to drop the V and put an edge between W and A. Otherwise, you don't. So this is the construction of my one-sided Biclique instance. So now we are going to see why this reduction is correct. So we're going to see the correctness of the reduction. Suppose you had a k-Clique, right? So you had these k guys that you can pick in the middle in V. And you know that there are k choose 2 guys on the right whose total neighborhood is this thing. And if you pick any k guys, then we have that the threshold graph gives us this, that they have a lot of common neighbors. And we're going to see how this goes through. So let's say you have V1 to Vk is a k-Clique in G. Now, because of the threshold graph, we have that, let's say that V1 to Vk has A prime as the set of common neighbors in A. Okay. Now, also note that if you take any A in A prime, then not only is V1 to Vk a common neighbor of this, but V1 to Vk, if you take any edge E, Vi, V prime, so you take any edge of your k-Clique, say it's the edge between vertex Vi and Vj. Now, both of these are going to be incident. So if you take this edge, it's going to be incident on the vertex. So let me go back to the picture. So here, let's say that this is the edge between Vi and Vj. So it's going to have a edge to Vi here and Vj here. And both of Vi and Vj have A as a common neighbor, right? So that's from this construction. So we have that every guy, which is a common neighbor of V1 to Vk in A is also a common neighbor of W in our new reduction of one-sided Biclique. So because there is this C4 formed. But we know that size of A prime is large. Size of A prime, because just from the completeness of the threshold graph property, we had that if you picked any k guys, you're going to have n to the 1 over k common neighbors. So that means that the common number of common neighbors of the k choose 2 edges of the k-Clique in A is going to be n to the 1 over k. And that gives us the completeness part. What about the soundness? So if you picked any k choose 2 guys in W, let's look at the new instance of the one-sided Biclique, and let's say A prime is the set of common neighbors. Now, at the same time, let's look at these k choose 2 guys, and let's look at the total neighbors in V prime, in V, and let's call it V prime, right? So we had this graph here. We picked any k choose 2 guys here. We know that let A prime be their set of common neighbors in our new instance here, for which we have this C4. But also at the same time, let V prime be the set of total neighbors, all the guys that you hit in V, using picking these k choose 2 vertices. Now we know that since there is no k-Clique, it's a soundness assumption, V prime is at least k plus 1. We just saw this earlier. So A prime, and on the other hand, if V prime is at least k plus 1, notice that A prime is just a subset of the common neighbors of V prime in the threshold graph, right? Because if you want to have the C4 and you can only enter through V prime, so you look at all the common neighbors of V prime, and A prime has to be at most the size of that. It can't be more. But we know that if you pick any k plus 1 guys, say like V prime, the number of common neighbors it can have is at most k plus 1 factorial. So the size of A prime can be at most k plus 1 factorial. And that gives us the reduction. So that gives us the theorem statement, which is that, again, there's a typo. If you start with a clique instance G, if G has a k-Clique, then you can find k choose 2 vertices in W, which correspond to the edges of the k-Clique, which have n to the 1 over k common neighbors. Whereas if G has no k-Clique, then any k choose 2 vertices you pick in W can have at most k plus 1 factorial common neighbors. So this is how Binkai's thing worked. But as I said before, I told you, just assume this magical graph exists. This is a very, very non-trivial graph. How do you build this threshold graph, right? Like, it's very hard to build it, but it turns out that it does exist. And let me say a few notes. I don't want to say how to build it, but let me just make a few notes on this. That if you look at the standard Eldridge-Renly model for random graphs, where you pick an edge with probability p, it has a very long, smooth decaying tail. So random graphs built from this property, regardless of the choice of p, will not satisfy the threshold properties that we need. So usually when we want to build threshold properties, we look at random graphs, but somehow what we need is too magical for it to exist. But recently, in unpublished work, it was found that if you took certain algebraic distributions, so you don't take every edge with probability p, but you associate a polynomial to every graph, and then you take a random polynomial and look at the graph corresponding to it, then it has better concentration bounds. So it does have the threshold property that we need. So there is a simple randomized procedure to generate such graphs. And in fact, there are these things called normed graphs in literature, and they get a slightly weaker property, and using randomness, we can find these threshold graphs. We can modify the construction a bit to get an explicit construction. So it is possible. You just had to use much more non-trivial objects. So just the simple things like codes was not enough. And it makes sense, as I said before. One-sided Biclique is an easier problem than MaxCover. So in order to prove hardness of approximation for an easier, computationally easier problem, we will need more non-trivial objects. So let me close the talk with giving a few comments on this technique as a whole. So what we saw today is coined as the threshold graph composition technique. And there are two ingredients that we need when someone wants to prove such a hardness approximation result. The first one is we need a threshold graph. So we need this, an extremal combinatorial object, and we need it. We can construct it sometimes very simply using codes, as we saw for MaxCover, or sometimes it has to be extremely non-trivial, as we saw for one-sided Biclique. And the second thing which we need, which is sometimes even more non-trivial and requires a lot more creativity, is the composition. So you have the input graph, you have a threshold graph. How do you mix the two things in order to get the final graph problem that you have of interest? How do you compose? So this is another part which we need. So once you are given these two, then so you can sort of break down this technique as finding these two objects. Now let's go to the threshold graph. So when we say we need a threshold graph, obviously each threshold graph has different threshold properties. So we need to formulate what threshold property we need. For the MaxCover instance, it was in the yes case you picked one from each, and in the no case you picked two from one supernode. And whereas in the one-sided Biclique, it was completely different, where you pick k vertices and look at their common neighborhood, and k plus 1 and you look at their common neighborhood. So different threshold, so each threshold graph has its own threshold property, and it's sort of defined, it's intertwined with the composition step that we are looking at. So once you come up with these threshold properties, the next question do you ask is, am I asking for too much, or does this graph actually exist? And then you sort of look up in literature or try to build them on your own. And sometimes, as it happens, it might be too hard to build these threshold graphs, in which case you can tweak the composition step you have between your input graph and threshold graph. So really, finding the threshold graph and finding the composition step is like a chicken egg problem. It's not clear which one to solve first. So you sort of try to play with them both simultaneously. So you try to tweak the composition step. So in fact, in Dinkilen's paper, he has a simpler reduction. So he built threshold graph using the standard Erdős-Rendley model, but he had to tweak the composition step to make it more complicated, slightly more subtle than the one I presented now. So you can always play around with these. And another thing you can play around is with the input problem. So here we started with the k-Clique problem, but maybe you can start with a more structured problem, something that people had worked on to prove hardness of. And if you start from there, then you might be needing less of the threshold properties, and the composition steps can be more easy. So we have these three things to play with, and these are the things we play with in order to make these threshold graph composition techniques work. So tomorrow's plan is going to be, I'm going to use these two in-approximability results we flew today to sort of prove results for set cover, Biclique. If I have some time, I want to also show some parts of even set and shortest vector problem, hardness approximation results. And also I'll sketch what we know right now for Clique from GAP-ETH. So that's my time for today.
Thank you so much, Karthik. Yeah, if anybody has questions, they can just unmute themselves and ask right away.
So, Karthik, can I ask?
Yeah, sure.
So the threshold property for one-sided clique, it was very sharp, n power 1 over k and k plus 1 factorial. Is it, did you really need that, or was it something available and so you picked it up, or how did it?
Right, so n to the 1 over k is it's just because we, even to get say k plus 1 factorial and 2 times k plus 1 factorial, right? So instead of n to the 1 over k, if I was just happy with say twice k plus 1 factorial, it would give you a gap of 2. This is almost, I don't know any construction that gives this and not the other one. Like you just get, either you get nothing or you get this for free all the way to n to the 1 over k.
I see.
And actually, if you open up some of the more constructions I was referring to, which are unpublished, you can see that it's just a blow up factor. If you wanted a gap of 2, then you have slightly small blow up like log factor. And to get n to the 1 over k, you blow up by a factor n. So that's the only thing. But the technique itself is inherently the same. Like you need these very deep techniques in order to prove things. I would say a lot of algebraic geometry.
Oh, okay. Thanks. So can you show me the slide on the existence of threshold graph? You had some remarks. I missed.
Right.
Yeah.
Here.
Okay, so what did you mean by semi-explicit? Maybe you said
Right, right. So non-graph. So let me go over to the. So non-graphs are these things known in literature, which are called Pele tape graphs, and what they have is the following. So they have the property that every k plus 1 vertices in V have at most k plus 1 factorial common neighbors. The thing they don't have is that the above statement, every k vertices in V have n to the 1 over k common neighbors, that's not true for them. What's true is that if you pick any k vertices with probability, say some function of k, 1 over some function of k, they have n to the 1 over k common neighbors. So it's not true for every, but with some probability, which only depends on k. Now, what you can do with that is that when we compose here in our previous thing, when we put this composition here, there was no way to associate the vertices of V from the input to the threshold graph, right? Like there was no ordering, we just did arbitrarily. Instead, if you do it with random, then you catch these k vertices that you care about with probability 1 over some function of k. And if you just repeat this, say some f of k times, then you get it with constant probability. So that's why I said semi-explicit, because you still use randomness, because you don't know which k vertices they are. Does that make sense?
Yeah, okay. Yeah, thanks.
Any more questions?
So I need to say that today was like probably the heaviest of the 3 lectures, and yesterday was the weakest. So tomorrow is going to be somewhat in between.
Okay. All right then. There don't seem to be any more questions as of now. All right. Thank you so much, Karthik. Thanks once again, and
Thank you.
thanks to the audience for being around.